Today, we're going to pull back the curtain on one of the most powerful yet invisible forces in our lives, electricity. Now, you probably think you have a decent idea of how it works, but trust me, by the end of this, you're going to see it in a completely new way. And it's all thanks to some surprisingly simple ideas. So, let's dive in.
All right, let's kick things off with a bit of a brain bender. What if I told you that the electricity charging your phone right now wasn't actually sent from some far-off power plant? What if it was just waiting inside the wire all along? It sounds kind of impossible, right? Well, the answer might just surprise you.
To make sense of this, picture this in your mind. You have a long, clear tube, and it is packed tight with marbles, from one end to the other. Now, if you push just one new marble into the front, what happens? Another one pops out the other end instantly. The push itself travels through that whole line in a flash, even though each individual marble barely moved an inch. And that right there, that's the whole secret. So to really solve our puzzle, we have to start by looking inside the wire itself. I mean, what's a simple copper wire really made of? And what in the world does it have to do with a tube full of marbles?
Okay, so here's the first thing we've got to get straight, the biggest misconception out there. Wires are not empty pipes waiting for electricity to be poured into them. Nope, they're actually jam-packed, just like our marble tube. But instead of marbles, they are filled with billions and billions of tiny particles called electrons. They are already in there, in the metal, in the wire, in your phone, just sitting there waiting for a push.
Okay, so if all these electrons are already sitting in the wire, what gets them to actually move? Well, it's not magic. It's really just a set of three basic rules that control how all electricity flows. They're called voltage, current, and resistance. Let's break them down one by one. First up, we've got voltage. The easiest way to think about voltage is that it's the push. It's the force, the pressure, that gets those electrons up and moving in the first place. If you don't have any voltage, all those electrons are just going to sit still. You know, a really great way to picture this is to think of a garden hose that's already full of water. The water is just sitting there, right? It's not going anywhere until you turn on the tap. Well, turning on that tap creates pressure. In electricity, that pressure has a name: voltage. Simple as that. No pressure, no flow. So if voltage is the push, then the next logical question is, well, how much is actually flowing? And that, my friends, is where current comes in. Current is the measurement of the volume. It tells us how many of those little electrons are zipping past this single point every second. Let's go right back to our garden hose. The current is just like the amount of water actually coming out the end. Is it a powerful gush or just a tiny little trickle? A high current means a ton of electrons are on the move, while a low current means, you guessed it, not so many are. And finally, we have resistance. The name kind of gives it away, but this is basically anything that gets in the way and slows down the flow of those electrons. You can just think of it as electrical friction. And for our trusty water hose, resistance would be like putting a kink in it, or maybe squeezing it so the pipe gets really narrow. The water can still get through, sure, but the flow is way less powerful. It's the exact same idea for electrons trying to move through a wire. So here it is, all laid out nice and neat. The electrons are like the little water droplets, the voltage is the water pressure pushing them, the current is how much water is flowing, and the resistance is anything that makes the pipe narrow. Seriously, if you can just remember this simple water analogy, you've basically nailed the fundamentals of how all circuits work. All right, now that we understand the push, the voltage, let's look at how that push is actually applied. Because it turns out there are two really different ways to get electrons moving. You can have a steady, one-way push, or you can have a super fast back-and-forth wiggle. And that's the whole difference between AC and DC.
But before we get into that, here's a quick question for you. When you flip a light switch, the light comes on instantly, right? Feels like it's moving at the speed of light. So how fast do you think those individual electrons are actually traveling down the copper wire? Just take a guess.
The answer is actually shockingly slow. A single electron just kind of drifts through a wire at a snail's pace, maybe just a few centimeters every second. So, wait a minute, how can that possibly be?
And this is where our marble analogy from the beginning comes back into huge way. Remember, the wire is already full. The power source doesn't have to send one electron all the way from the wall to the lamp. It just has to push the very first one. And that push, that wave of energy, travels down the whole line of electrons almost instantly, forcing the last electron, the one in the light bulb, to move. It's the energy that's fast, not the electrons themselves.
So this brings us back to those two types of push. First, you have direct current, or DC. This is what you get from batteries. It's simple. The electrons flow in one steady, continuous direction. But then you have alternating current, or AC, and that's what comes from our wall outlets. This is the weird one. The electrons don't actually travel all the way from the power plant to your house. They just wiggle. They wiggle back and forth right there in the wires you already have. The power plant is just pushing and pulling them, transferring energy over massive distances.
All right, it is payoff time. Now we get to use our new understanding of how electricity really works to solve a few everyday mysteries that, honestly, might have seemed a little confusing before.
First up, the absolute classic. We've all seen birds sitting on high-voltage power lines. So why in the world don't they get zapped?
The answer is actually pretty simple. Electricity always needs a complete path to flow, what we call a circuit. Since the bird is only touching one wire, the electrons go into its little feet, but then they have nowhere to go. There's no path through the bird to another wire or down to the ground. Now, if that bird were to stretch out a wing and touch a second wire at the same time, well, then zap, the circuit would be complete.
Okay, here's another one you've probably noticed. Why does your laptop adapter or your phone charger get so warm when you're using it?
The answer is one of our three main rules: resistance. It's all about resistance. As billions of electrons are being forced through that crowded little wire, they are constantly bumping and colliding with the atoms of the wire itself. Every one of those tiny collisions creates a little bit of friction, and all that friction adds up to create the heat you can actually feel. It's just a natural side effect of putting electricity into motion. So let's just lock in this new way of thinking about it. Wires are always full of electrons. Voltage is the push that gets them moving. Current is a measure of how much is flowing. Resistance is the friction that slows them down and creates heat. And that push can be a one-way street, like DC from a battery, or a back-and-forth wiggle, like AC from an outlet. That's really the heart of it. So there you have it, a completely new way to visualize how electricity actually works. And the real takeaway here is that even the most complex forces in the universe can often be understood with the right simple analogy. Which kind of leaves us with one final thought. What other invisible forces are shaping our world right now, hiding in plain sight, just waiting for a simple explanation? Makes you wonder, doesn't it?